G'day everyone. Day 3, transformer model parameter measurement. Whenever you're working with transformers or two inductors that have some kind of coupling with each other in a project, it's very useful to be able to extract a lumped parameter model of that transformer for, maybe you want to put it in a simulator like SPICE, or maybe you just want to like rationally work with that, or maybe you have a transformer that you can't dismantle and you want to know the turns ratio. In order to do that, the easiest way is basically to make some inductance measurements. So you can make inductance measurements of each winding, and then you can short circuit the other winding, or you can connect the windings in series either in phase or anti-phase, and by taking those values you can back out the coupling coefficient or the mutual inductance between the two windings. So mutual induction between two arbitrary conductors is essentially modeled as this mutual inductance. In the case of most transformers that are designed for power transfer, almost all of the inductance of each winding is the mutual inductance. So you try to minimize this thing called leakage inductance. So you've got a situation where basically the inductance that you see looking into this is the sum of this leakage inductance, which is a sort of the self-inductance of the winding that doesn't link the other winding, and then the mutual inductance, which is sort of shared between them, that fully links the flux with the mutual inductor in the other winding. In general, these two mutual inductances are different, but the coupling between two conductors is defined by this one, mutual inductance. So it's interesting, actually. The physics-wise, the mutual inductance between two, arbitrary conductors is essentially computed the same way as a self-inductance. So you could say self-inductance is just auto-mutual inductance, which, I guess why it's called self-inductance, right? Like, if you put in the geometry of the filament, or however you model the actual current distribution of a conductor with itself, that'll give you its self-inductance, and if you model it with another conductor, that'll give you the mutual inductance between them. But I digress. In general, what you can do with the in-phase and anti-phase measurement is probably the easiest to understand. Individually, like if you imagine the other half of the transformer just wasn't there, then what you're looking at is just the inductance of that winding as if it was in free space or with the core. And that's true for, the primary and the secondary, I've called them L1, L2. So if you hook them up together, naively, if the core wasn't there and they didn't have any flux linkage with each other, the total inductance would just be L1 plus L2. But because of this mutual inductance between them, the mutual inductance counts on both sides of the transformer, so you actually get L1 plus L2 plus 2 mutual times the mutual inductance. And when you connect them antiphase, then you get L1 plus L2 because they don't link any flux with each other, and then you get minus twice the mutual inductance. So if you subtract the in-phase, the outer phase from the in-phase value, then you'll get 4 times the mutual inductance. The actual two self-inductances will cancel. And interestingly, actually, if you add them, then the mutual inductances will cancel and you get twice the sum of the two self-inductances. But that's a useful check, and I don't think too many people use that. They just kind of like connect them in phase, connect them anti-phase, subtract those values and divide by 4 and assume that's the mutual inductance. So then the ratio of that mutual inductance to the geometric mean of the two inductances is this coupling coefficient. And the coupling coefficient is sort of the amount of total inductance, the amount of the mutual inductance that the total inductance of that winding represents, or affects, I guess you could call it. So you could say M1 is like 1/k of the total L1 inductance, whereas the actual leakage inductance is like 1 minus k of that the inductance that you measure just looking into the winding. The useful thing about this is that it gives you this number between 0, absolutely no coupling, and 1, perfect coupling, and you can use that to basically work out a whole bunch of interesting things about the transformer. In particular, in power transformers, it's kind of important for the short circuit current, because if you short, imagine you short this, so you're reflecting essentially a short, although you'll have this leakage inductance, so you'll have twice the leakage inductance, and that will limit the input current that this will pull. Worst case, if this is shorted. If it's open circuit, then it will pull reactive power, but I digress. This is not a lesson in AC circuit stuff. This is just about how the heck you actually measure a random transformer that ends up on your desk. So this brings up the second way you can do this, which is to simply short one winding and measure the inductance. So when you're measuring the inductance of this with open circuit, you get some value, you short this and it will drop. And the amount that it drops is sort of a reflection of the fact that this magnetization, or that the mutual inductance has been gone away or been reduced by mirroring this leakage inductance over to this side of the transformer. But in practice, you can use that by, I've called it L1SS for short circuit. So you can measure that value pretty straightforward, right? So you measure this, short this side, see what the result is, and you can take that value and back out the coupling coefficient from that, because it's 1 minus that ratio between the lower value you get after when you short it and the open circuit value. Take the square root of that, you get the coupling coefficient. So yeah, math, I know everyone's probably tuning out at this point. What does this look like in practice? Alright, so this is a transformer off the shelf, actually from Amazon. It's a 600 to 600 ohm audio coupling transformer. I measured it at 1 kilohertz. It has DC resistances of about 135, 136 ohms, somewhere around there. We're going to ignore the resistances here. The inductances looking into each side of the transformer with the other side open are about 404 millihenry. When you short the opposite winding, you get about 1.37 millihenries. So if you do the math using this, ratio of the shorted and unshorted secondary, then you get a coupling coefficient of 0.9983. So almost perfect. Essentially all of the flux from the primary is being linked into the secondary. If you use that and then try and back out the mutual inductance and the mutual inductance on this side of the transformer, then you get these values here, which is kind of what you'd expect. And if you do that for the other side, you get these values. The coupling coefficient should be the same. If they're not, then it's probably a measurement error, though they should be very close to each other. You can also do it the other way, where here I connected them up in series and I measured 1.6 henries, and when I connected them antiphase, I got 327.4 microhenries, so a big drop. Again, do the math. That gives you a mutual inductance of 404.17, so just slightly less than the harmonic mean, or either winding, really. I mean, it's got to be generally less than each winding. And you also get a similar coupling coefficient. It came out a little higher. I don't know if that's measurement error or just because of some things like capacitance and unmodeled behavior in the transformer. But this is kind of like a pretty typical result that you'll see in a strongly coupled transformer like a power transformer. What's uninteresting about this is that this is a one-to-one transformer, right? Like it has the same amount of turns on both sides. You can see that by the ohmic resistance is approximately the same. When you do the math on the ratio of the impedances, they're inductances, or I mean by saying impedances, then again you get an alpha, which is the turns ratio of 1, because that's good, right? Like we proved that this is a one-to-one transformer. We proved that it has really good coupling. This doesn't measure losses, obviously, in a direct sense. There's nothing about resistances here. This is purely about induction. So a more interesting example might be this. So this is, a kind of homemade transformer. It's not particularly well coupled. It has a coupling coefficient of about 0.16 something. And it's just simply 10 turns and 20 turns glued down, to a piece of plastic here, and go through the same procedure. DC resistances there for interest. You can see there's approximately twice the amount of copper in this side than there is in this side. The inductance here is almost, I mean, it's not quite 4 times more, which actually makes you wonder about whether or not this actually is 20 turns or 19 turns, but we'll get to that in a minute. And when you short it, you can see the inductance doesn't drop anywhere near as much as the where in this guy over here, when we shorted the secondary, a great deal of the inductance went away. In here, only a fairly small amount of the inductance vanished. And if you use that and do the math, you get a coupling coefficient of 0.16, because these are weakly coupled, right? There's only the whatever flux comes out of this guy and goes through this guy is joining these two coils together. The rest is just being returned back as self-inductance, and that is what the leakage term is. So you do the math, this is the leakage inductance, right? And so this is basically 1 minus K times the open circuit inductance, and the mutual inductance that you see, looking into this, is 1.7-ish microhenries. The main mutual inductance between these two windings is about 3.4 microhenries. On this side, the mutual is 6 point. And this is kind of what you'd expect, maybe like with the turns ratio. Again, leakage inductance, actual shared mutual or magnetizing inductance, depending on how. I mean, there isn't actually a core here, so I wouldn't call it what's traditionally called magnetizing inductance, but it's mutual and magnetizing inductance are kind of synonymous when you have a high mu core, but they're not exactly the same. So we use the other method where we add them in phase, we connect them antiphase, we get the true mutual inductance between the windings out of that, and we do the math on that, and we get a coupling coefficient. It's pretty close, like 0.161, 0.163, 0.59. They're all saying it's about 0.16 something. I don't know, again, if this is measurement error. I had to measure this transformer at a higher frequency at 100 kilohertz. I don't know if my bridge is kind of crappy there, or if the distributed capacitance and other things are starting to become an issue. To do this properly, obviously you need a more sophisticated model, but again, we're kind of limited by our very straightforward model here, where we're just assuming it's lumped inductors with a certain amount of linked flux. Anyway, the result is you have L and M and K. So these are the kind of numbers maybe RDC as well, that you want to put into your SPICE model if you're actually going to try and use these in practice. So if you have some random transformer, this is a good place to start. Just measure the inductances, short the opposite winding, connect them in series antiphase, write all those numbers down, do the math, and it's not particularly complicated. The easiest one to remember is probably this: subtract the in phase and antiphase and divide it by 4, and you get the mutual inductance. You can check it with it's half of the sum of the inductances, and the mutual inductance being this ratio harmonic mean thing is also pretty straightforward to remember. But the turns ratio thing is also quite useful if you just want to know how much it steps up or steps down without just measuring some known, inject a known voltage into one side, measure the known voltage out of the other side, the measured voltage out of the other side, you get the turns ratio. You can do it using just an instrument like this instead of having to dig out the oscilloscope. Alrighty, that's a little more math heavy maybe than I would normally go, and I didn't really show you doing this in practice, but it's not particularly exciting. I did make up a little shorting lead that I use for just this kind of thing. This obviously has a little bit of inductance, and for this transformer maybe starting to become a significant amount of inductance. So if you minimize its loop area when you're making the measurement, or when you're just shorting, you just use the clip to like short both of them together, or anything you can do to kind of minimize those additional extraneous amounts of inductance and capacitance in the circuit, the better the results you'll get. But the other thing, one more thing I guess you need to be careful about is if you are measuring this at higher frequencies, is that your transformer hasn't had some kind of resonance happening. So the distributed capacitance of the windings, or any kind of lump capacitance across the windings, can mean that you're no longer dealing with an inductor anymore. But in general, if you measure the transformer near the frequencies that you're going to actually use it at, you'll get the best results, right? Because that's actually realistic. More sophisticated models require some kind of measurement instrument or a bridge that can sweep it over frequencies, and that will give you a lot more information because you can fit a more sophisticated multi-parameter model to the actual, essentially the impedance measurement that you get, like the complex impedance, the full magnitude and phase information. Alrighty, we'll talk about something completely different tomorrow. Bye.